I see you're tackling a problem involving least angle regression, or Lars, specifically in scenarios where you have many more features, variables describing your data points, than data points themselves. This is a common challenge in machine learning, often referred to as the high-dimensional, low sample size problem. Lars is a clever algorithm designed to handle this situation effectively. We're investigating how Lars behaves when features significantly outnumber data samples. This is an important context to consider because LARS's performance can change depending on these data characteristics. I'm using scikit-learn, a popular Python library, and applying Lars. The core issue is that the number of features, p, is far greater than the number of data samples, n. We must evaluate the effects of this imbalance on LARS's behavior to understand what conclusions we can draw from it. This option states that Lars automatically performs feature selection, meaning that it essentially decides which features are most important and ignores the rest. Option B claims that Lars always finds the best possible solution, the least squares solution, if given enough time. Here, we are comparing LARS's computational cost with ordinary least squares, OLS, a more traditional method for regression. This option brings up the issue of overfitting, a major concern in machine learning where the model fits the training data too well but performs poorly on new, unseen data. I'm presenting a problem about using least angle regression, Lars, in scikit-learn with many features and few samples. We'll explore how Lars behaves in this situation. I want you to think critically about how Lars handles feature selection, computational cost, and the risk of overfitting. Get ready to select all the true statements. This is the core of the problem. We are given a scenario where the number of features, p, is far greater than the number of samples, n, which is a common situation in high-dimensional data analysis. We use Lars, a regression technique, and examine its properties. We'll analyze how this affects its feature selection abilities, computational efficiency, and its proneness to overfitting. Think of it like trying to find the best recipe using many more ingredients than you have taste testers. Lars, in a nutshell, iteratively adds features based on their correlation with the remaining errors. When there are many unimportant features, Lars cleverly assigns them coefficients close to zero, effectively performing feature selection. It's like a smart chef discarding ingredients that don't improve the dish's taste. Ideally, yes, Lars creates a path that explores all possible combinations of features. However, in practice, getting the exact least squares solution might not always be feasible. Early stopping is a common practice to avoid overfitting, trading off perfect convergence for better generalization. Think of it as aiming for the bullseye, but stopping when you're close enough to prevent excessive adjustments. This statement is actually false. OLS involves solving a potentially massive system of equations, which becomes computationally very expensive when dealing with many more features than samples. Lars is much smarter. It only incrementally adds features, making it significantly more efficient in high-dimensional scenarios. It's like comparing a direct route, OLS, with a more efficient, step-by-step approach, Lars. Overfitting is a major concern when features greatly outnumber samples. Even though Lars does feature selection, the risk of overfitting still exists. The model might learn the quirks of the training data too well, thereby failing to generalize accurately to new unseen data. It's like a student memorizing the answers to a practice test perfectly, but struggling on the real test because they didn't grasp the underlying concepts. I've determined that statements A, B, and D accurately describe LARS's behavior in the given situation. Remember, Lars offers a powerful approach to high-dimensional data, but it's important to be mindful of its potential for overfitting. I'm focusing on the least angle regression, LAR, algorithm, specifically its behavior when dealing with datasets where the number of features, p, significantly exceeds the number of samples, n, a situation common in high-dimensional data analysis. We'll explore how LAR handles this challenging scenario. I think we will understand this better together. I've got a multiple-choice question for you about LAR. It tests your understanding of the algorithm's properties and behavior in high-dimensional datasets. Get ready to see if your knowledge of LAR's strengths and weaknesses matches mine. I'm presenting a scenario. You're using the LAR algorithm, from the scikit-learn library, on a dataset where the number of features far surpasses the number of samples. The question is, which statements accurately describe LAR's behavior in this type of situation? Let's dive into the options, one by one. This statement suggests that LAR automatically performs feature selection. I want to know if you agree with this assertion. The key is to understand how LAR adds features, and what happens to the coefficients of less important features. Here, I'm checking your understanding of the convergence properties of LAR. Does LAR always find the least squares solution? I think the answer is a little nuanced and needs further exploration. This statement compares the computational costs of LAR and ordinary least squares, OLS, regression in high-dimensional settings. Do you think LAR is more computationally expensive? I'm interested in your understanding of the computational efficiency of both algorithms, especially when dealing with lots of features and limited samples. This statement focuses on LAR's susceptibility to overfitting. In high-dimensional settings with limited samples, does LAR's feature selection prevent overfitting? Or is it still prone to overfitting? Let's discuss this important point regarding the risk of producing a model that fits the training data too well, but generalizes poorly to new data. This concludes the question. Let's review your responses and explore any remaining doubts about LAR behavior in high dimensions. I hope we're both satisfied with the explanation provided. This question asks you to think critically about how the least angle regression, LARS, algorithm behaves when dealing with a dataset that has many more features, P, than data points, N. We'll examine each statement to see if it accurately reflects LARS's properties in such a high-dimensional setting. Let's dive in. LARS works by adding features to the model one by one, based on how strongly they correlate with what's left unexplained. When dealing with lots of features, many will be unimportant. Therefore, LARS effectively performs feature selection by assigning very small, or near zero, coefficients to these unimportant features. Pretty cool, right? LARS iteratively builds up a solution by adding features. Ideally, with enough iterations, LARS will get extremely close to the least squares solution. However, in practice, I might stop it early to prevent overfitting. It's a balance between accuracy and avoiding overfitting. Overfitting happens when a model learns the training data too well and performs poorly on new data. Even though LARS does feature selection, if you have far more features than samples, it's still possible to overfit. It is like trying to fit a really complicated curve through a few data points. Think of it like this. Too many features can lead to a model that's too specific to your training data. In summary, this problem tests your knowledge of how LARS works with many features and relatively few data points. I want you to understand LARS's capabilities and limitations. Knowing this is really important for choosing the right modeling technique for your dataset. Let's tackle the statements one by one. Ordinary least squares, OLS, solves a system of linear equations. For high-dimensional data, this process can become computationally very expensive. LARS, on the other hand, iteratively adds features. This usually means LARS will be less computationally expensive than OLS in high-dimensional settings. Remember that computational efficiency can be important when working with very large datasets. See, this section introduces least angle regression, LAR. LAR is a method for fitting linear models to high-dimensional data, situations where you have many more variables than observations. I'll explain more about its unique properties in the next sections. Okay, let's tackle this. You're using LAR from Sklearn and dealing with a dataset having tons of features, P, but relatively few data points, N, where P is way larger than N. The quiz asks you to figure out which statements about LAR's behavior in this situation are true. I think this statement is likely true. LAR cleverly adds features one by one based on how well they correlate with the remaining prediction errors. With many irrelevant features, LAR tends to give these features near zero coefficients, effectively ignoring them, which is exactly feature selection. This is a bit tricky. In theory, LAR works its way toward the least squares solution. That's what OLS, ordinary least squares, regression finds. In practice though, it's better to stop before going all the way to avoid overfitting. I'd say this is largely true, but with a caveat about early stopping. I'd agree that this is true. With many features and few data points, there's a higher risk of your model capturing random noise in your data and performing poorly with new, unseen data. The fact that LAR does feature selection helps, but overfitting is still a real risk if you're not careful. This sets the stage. I'm looking at a high-dimensional data problem. High number of features compared to observations. This is a context that's important to understand. I'm focusing on the least angle regression, Lars, algorithm. Lars is a regression technique especially useful when you have many more features than data points. Think of it as a clever way to deal with a dataset that has lots of variables but not much data. I'm examining the case where the number of features, p, is much greater than the number of data samples, n. This is a typical high-dimensional data setting, which poses unique challenges for many machine learning algorithms, including Lars. I'm checking to see if Lars always finds the best fitting line, like ordinary least squares, OLS, does. It turns out it's almost true. Lars iteratively refines its solution and, theoretically, gets increasingly closer to the OLS solution as you let it run longer. However, in practice, early stopping is used to improve the model's performance, avoiding potential overfitting to the training dataset. I'm comparing Lars to OLS computationally. I'm focusing on the computational cost of each method. I find that Lars is generally more efficient when you have more features than samples. OLS needs to solve complex equations, while Lars adds features incrementally, making it faster for this type of dataset. I'm looking at the statements about how Lars behaves with high-dimensional data. This is a multiple-choice question testing your understanding. I'm exploring the risk of overfitting with Lars. With many more features than samples, Lars can potentially memorize the training data rather than learning general patterns. This is a significant risk in high-dimensional settings even if Lars automatically selects features. I'm analyzing Lars's feature selection capability. It is true that Lars does implicitly perform feature selection by giving small or zero weights to less important features. I'm focusing on least angle regression, or Lars, a clever algorithm that's especially useful when you have many more features than data points. Think of it like trying to find the best combination of ingredients, features, for a recipe with limited taste tests, data points. Lars cleverly adds ingredients one by one, always choosing the one that best explains the remaining taste we haven't captured yet. This is particularly handy when I have a high-dimensional dataset. I'm going to evaluate each statement based on how Lars works with a high-dimensional dataset, where the number of features greatly surpasses the number of data samples. We'll analyze each choice individually using my understanding of the algorithm and its properties in the context of high-dimensional data. This statement is true. Lars has an inherent ability to perform feature selection. It does this by gradually adding features to the model, focusing on those that most strongly correlate with the remaining unexplained data. This often results in many features having near zero coefficients, effectively removing them from the model. I would say that this property is a key strength of Lars in the high-dimensional setting. This is generally true, but it depends on my interpretation. Lars builds a solution path that eventually moves toward the least squares solution. However, it might not achieve it exactly due to numerical precision limitations. It is better to consider this true in theory, although in practice we often stop early to avoid overfitting. This is false. Ordinary least squares, OLS, regression is notoriously slow and can be computationally expensive, or even fail, in high-dimensional cases, involving large matrix inversions which are likely to be unstable. Because Lars adds features one by one, it's computationally more efficient than OLS in this situation, making it a better choice for such datasets. This statement is true. While Lars helps by doing feature selection, if I have many more features than data points, there's still a high risk of overfitting. The model can get too good at explaining the training data but fail to generalize well to new data. Regularization techniques are often needed to help mitigate this overfitting tendency.